So the major question for this unit is going to be, why exactly do molecules exist in the state that they do? So why is water a liquid, and why is carbon dioxide a gas? And in order to answer that question, we actually need to understand how those molecules exist in the real world. Specifically, what shape do they assume? And in order to answer that question, we are going to have to learn how to draw the Lewis dot structures for these molecules. In order to do that, we need to quickly review how to determine the number of valence electrons each element has. So just as a quick review, remember, to determine valence electrons, we can use the periodic table. And we know that group 1 right here has 1 valence electron. We know that group 2 has 2 valence electrons. Remember, from this group here, for the most part, it's 2 valence electrons, because remember, the d orbital is 1 energy level lower than the s orbital, but we don't tend to use these metals, and I'll explain why in a second. 3 valence electrons, 4 valence electrons, so it just increases as you go across. Now, I just said, as I'm writing this out, I just said we don't tend to use these elements because they're metals. And what I meant by that is that for the compounds we are going to be creating in a second using covalent bonding, right? Water, carbon dioxide have covalent bonding. You need 2 nonmetals. So we're specifically going to be looking at this region over here, right? To the right of your staircase, and then also hydrogen. Okay, so that's how you determine valence electrons. Now I'm going to show you how to draw the Lewis structure. And there are clear 4 steps that you need to take every single time you create a Lewis dot structure or a Lewis dot diagram. Okay? The first step that you have to do, you have to count your number of valence electrons. Okay. So instead of me moving on, I'm going to show you with the first example. Okay, so for water, I have to count my number of valence electrons. All right, hydrogen, if you look at your periodic table, has 1 valence electron, but there are 2 of them. And then oxygen, if you look at your periodic table, has 6 valence electrons. So this is going to be a total of 8 valence electrons. So that's step 1. Let's go to our next step. That was C. S, I have to share electrons between atoms. Okay, so let's see what that will look like. Go back to water. Notice I have 2 hydrogens and 1 oxygen, so I'm going to put oxygen at the center because there's only 1 of them, and I'm going to share electrons between oxygen and each of the hydrogens. Now keep in mind, this line, when we discussed this earlier when we were looking at covalent bonding, this line represents 2 electrons. So oxygen is sharing 2 electrons with this hydrogen, and oxygen is sharing 2 electrons with that hydrogen. Okay, so that's step 2. The next step is to add lone electrons so that all atoms have an octet. Now there's one exception to this, and that is hydrogen. Remember, the noble gas closest to hydrogen is going to be helium, which has 2 valence electrons. So hydrogen is actually content with just 2 valence electrons. Okay, so let's see that play out right now. So let's go back to our example. We've got water. So I'm going to add electrons to my outer atoms first, and then electrons to my central atom, my inside atom here. So remember, every atom wants 8 valence electrons except for hydrogen, which wants 2. Right now, with this bond right here, this covalent bond, this represents 2 electrons. So hydrogen actually already has 2 electrons, which it's sharing with oxygen. And this hydrogen also has 2 electrons already. So those are content. Oxygen needs to follow the octet rule. So right now it only has 2 electrons here and 2 electrons here. So it has a total of 4 electrons, which means it needs an additional 4 electrons to get 8 valence electrons. So there are 2 different ways I can draw this. One is I can draw it like this. I'm going to add 2 electrons on top and 2 electrons on bottom. Or what you'll find yourself doing when you're drawing this, okay, is you'll add a line and another line. These lines represent these 2 electrons. So if you want to draw it this way, that's perfectly fine. Now, if you drew it this way and left it, that would actually be wrong, and you'll understand why in a couple of sections. But we need to take into account the Vesper model. Now, what the Vesper model tells us is that molecules are going to assume the shape that minimizes electron repulsion. So basically, these electrons here and these electrons here are going to actually repel the hydrogen atoms. And so in order to minimize those repulsions, the molecule itself is going to take on a shape that minimizes that. Now, I don't expect you to be able to pull this out of your hat and know what this shape is going to look like. And so for the next couple of lessons, you guys will have access to the following website. So here's the website here. Okay, so this website was provided to you on Schoology. If you go and click Model, okay, I'm going to actually recreate the model that I have for water. So remember, water has 2 hydrogens. I've got 2 hydrogens right here. Okay? And then it also has 2 lone pairs of electrons. Let's quickly look at that. You see 2 lone pairs. One here, the second one here. And so when I create this, I'm going to add 2 lone pairs of electrons. Okay? So this is using the Vesper model. Notice I've got 2 pairs of electrons on top, and then my 2 atoms are pushed downwards into this bent shape, okay? So when you draw this, you can't draw it with looking linear like we did before. So how could I draw this? Well, this is how I would draw this molecule using the Vesper model. With the hydrogens facing downwards, okay, with the hydrogens down like this, and then 2 lone pairs of electrons on top like that. That is my best approximation of what the model looked like. Okay? So this is used, you can create that first when you're following the steps that I just outlined, but your final product needs to look like this, and it'll really make sense next section when I explain why we need this shape versus showing it linearly. Okay? Now I'm not quite done. Let's look at the last step. So for the last step, I need to check the number of valence electrons I used. So I need to check the number of valence electrons. Okay, so let's do that, and then we'll move on to the next example. So if I look at water here, I should be using 8 valence electrons. Let's see how many I'm using. Remember, each covalent bond represents 2 electrons, so I'm using 2 here, so a total of 4. And then each line represents 2 electrons. So 2, 4, 6, 8. I'm using 8 valence electrons. I should be using 8 valence electrons, so I'm good to go. Okay? For the next example, let's talk through the steps as we do it. So the first thing I need to do is count valence electrons. So phosphorus has 5 valence electrons. Bromine has 7, but there are 3 bromines. So I'm going to have a total of 26 valence electrons. Now I'm going to draw out my atoms. I'm going to have phosphorus. Remember here we're not using Vesper model, so you can draw this however you want to begin with. Okay. And my next step is S, share electrons. So I'm going to share electrons, share electrons, share electrons. Okay. Then I need to add lone electrons. So let's do that. And I'm going to represent them with lines rather than with dots. So right now, I'm going to work on my outside atoms first and then my central atom. Okay? So right now, bromine has 2 valence electrons from this covalent bond, but it wants 8. So here's how I would draw it. I'm going to draw, so I've got 2 already, 4, 6, 8. So keep in mind, do not draw a lone pair right here because then it just looks weird because it's right next to a covalent bond. So when you're drawing lone pairs of electrons, you're going to have 4 different sides on that atom where you can put your lone pairs of electrons. I would just put them away from the covalent bonds like I did. Okay, this bromine here has 2 already, so it needs an additional 6, so 2, 4, 6. This bromine has 2 already, so it's going to need 6 in order to get that perfect octet. Now my bromines are happy, and I need to make sure my phosphorus is happy as well. So I've got 2, 4, 6 electrons around my phosphorus right now, so I need 1 more lone pair of electrons to make sure it's content. All right, so for PBr3, I have 3 bromines on my central atom, so it looks like this, okay? But then I also have 1 lone pair of electrons. So here's the shape here, you can look at it. Notice the lone pair of electrons before, when I didn't have the lone pair, looked like this, they were all on the same plane, okay? But as soon as you add that lone pair of electrons, this is the shape that you have. So I'm going to show you right now how I would draw this, but notice you've got 1 lone pair of electrons on top and then 3 moving downwards. All right, so after looking at that model, let's redraw this. You're going to have phosphorus here, and remember you have your 3. This is my best way of drawing the 3D diagram, right? You had the 3 going in the opposite directions being pushed downwards. That's going to be my bromines. Okay. I'm going to add on my lone pairs of electrons. I'm not going to get rid of those. I still need to show them. And then the lone pair of electrons on phosphorus, as you saw in the simulation, is going to go on top like that. Okay, so that's my best way of drawing it. Obviously, I'm not an artist, so if you can do a better representation of what you saw, awesome. My last step, I need to count my total number of electrons that I've used and check to make sure that I'm using the correct number. So let's check. I'm going to start with the bromine. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm using 26, and I should be using 26. So I'm good to go.